question revolves around National Electrical Code, or NEC, Table 310.15 Tor-4 and whether separate neutral conductors should be counted for derating purposes. The answer is yes. If you pull a separate neutral conductor for each ungrounded conductor, you do not count the neutral for derating purposes. To understand this fully, we need to delve into the context of conductor ampacity, derating factors, and the specific conditions outlined in the NEC. Ampacity refers to the current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors can affect a conductor's ampacity, including the ambient temperature, the number of current-carrying conductors in a raceway or cable, and the conductor's insulation type. When multiple current-carrying conductors are bundled together, the heat generated by each conductor can raise the overall temperature within the raceway or cable. This increased temperature can reduce the ampacity of the conductors. To compensate for this, the NEC requires that the ampacity of the conductors be derated. Derating involves reducing the allowable current that a conductor can carry based on the number of current-carrying conductors in a raceway or cable. The NEC provides tables and guidelines for determining the appropriate derating factors. Now, let's focus on Table 310.15 Tor-4. This table addresses the derating of neutral conductors in specific situations. In a three-wire circuit consisting of two-phase conductors and a neutral conductor, where the neutral conductor only carries the imbalanced current from the phase conductors, the neutral conductor is generally considered to be a current-carrying conductor for derating purposes. However, there's an exception to this rule when dealing with nonlinear loads. Nonlinear loads, such as electronic devices and fluorescent lighting, can generate harmonic currents. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. In a three-phase system with nonlinear loads, the third harmonic currents and multiples thereof, such as the 9th and 15th harmonics, tend to add up in the neutral conductor. This can cause the neutral conductor to carry a significantly higher current than it would in a balanced linear load system. The NEC recognizes this phenomenon and requires that the neutral conductor be considered a current-carrying conductor for derating purposes in these situations. However, if you run a separate neutral conductor for each ungrounded conductor, this situation changes. In this configuration, each phase conductor has its own dedicated neutral conductor. As a result, the harmonic currents do not accumulate in a single neutral conductor. Instead, they are distributed among the separate neutral conductors. Because the harmonic currents are distributed, the neutral conductors do not carry a significantly higher current than the phase conductors. Therefore, the NEC allows you to not count these separate neutral conductors for derating purposes. This exception is outlined in NEC Table 310.15 Tor-4. It's important to note that this exception only applies if the neutral conductors are truly separate and do not combine at any point before reaching the load. If the neutral conductors are combined, then they must be counted as current-carrying conductors for derating purposes. Furthermore, the size of the neutral conductor must still be adequate to carry the maximum unbalanced load current. The NEC specifies requirements for sizing neutral conductors based on the expected load current. It's crucial to consult the NEC and other relevant codes and standards for specific requirements and to ensure that all electrical installations are performed safely and in accordance with applicable regulations. Here is an example to illustrate this concept. Imagine you have a three-phase, four-wire system supplying power to a commercial building with a significant amount of electronic equipment. The system operates at 208 volts. You have three-phase conductors, each carrying 20 amps, and a single neutral conductor. Because the building has a lot of electronic equipment, there are significant harmonic currents present in the system. These harmonic currents cause the neutral conductor to carry 30 amps. In this scenario, you would need to consider the neutral conductor as a current-carrying conductor for derating purposes. However, if you were to run a separate neutral conductor for each phase conductor, the harmonic currents would be distributed among the three neutral conductors. In this case, each neutral conductor would only carry 10 amps of harmonic current. Because the harmonic currents are distributed, you would not need to count the separate neutral conductors for derating purposes, assuming each phase conductor still carries 20 amps. This can have a significant impact on the size of the conductors required for the installation. If you had to count the neutral conductor for derating purposes, you would need to use larger conductors to compensate for the reduced ampacity. However, if you do not have to count the neutral conductor, you can use smaller conductors, which can save you money and reduce the size of the raceway or cable required. It's important to carefully consider the load characteristics and the potential for harmonic currents when designing electrical systems. By understanding the NEC requirements for derating neutral conductors, you can ensure that your electrical installations are safe and efficient. In summary, according to NEC Table 310.15 Tor-4, if you pull a separate neutral conductor for each ungrounded conductor, you generally do not need to count the neutral conductors for derating purposes. This exception applies when the neutral conductors are truly separate and the harmonic currents are distributed among them. However, you must still ensure that the neutral conductors are properly sized to carry the maximum unbalanced load current. Always consult the NEC and other relevant codes and standards for specific requirements and to ensure that all electrical installations are performed safely and in accordance with applicable regulations. The number of current-carrying conductors affects the ampacity of the conductors in a raceway, cable, or earth. When the number of current-carrying conductors exceeds 3, the allowable ampacity of each conductor must be reduced as specified in Table 310.15.3. A neutral conductor that carries only the unbalanced current from other conductors of the same circuit is not required to be counted when applying the provisions of Table 310.15.3. In a 3-wire circuit consisting of 2 phase wires and a neutral, the neutral only carries the imbalance of the 2-phase conductors. For example, if one phase conductor has a load of 15 amps and the other phase conductor has a load of 10 amps, then the neutral conductor will carry the difference of 5 amps. The neutral conductor does not need to be counted in this scenario. A neutral conductor in a 3-phase, 4-wire circuit used to supply a nonlinear load shall be counted as a current-carrying conductor. Nonlinear loads introduce harmonic currents into the electrical system. Harmonic currents are multiples of the fundamental frequency, which is 60 Hz. Common nonlinear loads include electronic ballasts, variable frequency drives, and other electronic devices. The triplen harmonic currents, that is, harmonics that are odd multiples of 3 such as the 3rd, 9th, and 15th, are additive in the neutral conductor of a 3-phase system. The result is that the neutral conductor can carry more current than the phase conductors. For this reason, the NEC requires that the neutral conductor be counted as a current-carrying conductor. In a 3-phase, 4-wire circuit used to supply electric discharge lighting, a neutral conductor that carries as load which consists of primarily 3rd harmonic currents shall be counted as a current-carrying conductor. Electric discharge lighting is a type of lighting that produces light by passing an electric current through a gas. Examples of electric discharge lighting include fluorescent, metal halide, and high-pressure sodium lighting. Electric discharge lighting produces significant 3rd harmonic currents, which flow in the neutral conductor. As a result, the NEC requires that the neutral conductor be counted as a current-carrying conductor. On a 4-wire, 3-phase Y circuit where more than 50% of the load consists of nonlinear loads, the neutral is considered a current-carrying conductor. If more than 50% of the load is nonlinear, then the neutral conductor will likely carry a significant amount of harmonic current. For this reason, the NEC requires that the neutral conductor be counted as a current-carrying conductor. A neutral conductor is not required to be counted when applying the provisions of Table 310.15.3 for circuits in which the load consists of electric discharge lighting or nonlinear loads when a qualified person designs the system so the 3rd harmonic is minimized. If the 3rd harmonic is minimized, then the neutral conductor will not carry a significant amount of harmonic current. In this case, the neutral conductor does not need to be counted as a current-carrying conductor. Derating factors for conductors are specified in Table 310.15.3 of the NEC. These factors are applied to the allowable ampacity of conductors to account for the effects of elevated ambient temperatures and the presence of multiple current-carrying conductors in a raceway or cable. The number of current-carrying conductors in a raceway or cable is a significant factor in determining the appropriate derating factor. The more current-carrying conductors there are, the greater the heat generated within the raceway or cable, and the lower the allowable ampacity of each conductor. The NEC defines a current-carrying conductor as a conductor that carries current under normal operating conditions. This includes phase conductors, neutral conductors in certain situations, and equipment grounding conductors under fault conditions. Grounding conductors are generally not considered current-carrying conductors for derating purposes, as they only carry current during fault conditions. However, there are exceptions to this rule, such as when grounding conductors are used to carry neutral current in certain types of systems. Some key considerations when determining whether a neutral conductor should be counted as a current-carrying conductor for derating purposes. Firstly, the type of load being served. Nonlinear loads, such as electronic devices and fluorescent lighting, generate harmonic currents that can significantly increase the current flowing in the neutral conductor. Secondly, the wiring configuration. If the neutral conductor is shared by multiple circuits, the harmonic currents from those circuits can add up in the neutral conductor. Thirdly, the design of the electrical system. If the system is designed to minimize harmonic currents, the neutral conductor may not need to be counted as a current-carrying conductor. The NEC provides specific guidelines for derating conductors based on the number of current-carrying conductors in a raceway or cable. It is important to consult these guidelines to ensure that conductors are properly derated to prevent overheating and potential fire hazards. The NEC also provides specific requirements for sizing neutral conductors. The size of the neutral conductor must be adequate to carry the maximum unbalanced load current, as well as any harmonic currents that may be present. In some cases, the NEC may require the neutral conductor to be larger than the phase conductors. The NEC is a complex and constantly evolving document. It is important to stay up to date on the latest changes to the code to ensure that electrical installations are performed safely and in accordance with applicable regulations. Consulting with a qualified electrical engineer or contractor can help to ensure that electrical systems are designed and installed in accordance with the NEC and other relevant codes and standards. Always prioritize safety when working with electricity. Follow all applicable safety procedures and use appropriate personal protective equipment.